Okay, thank you so much, Mr. Chairman. And we will continue with a work on the adhesive bonding of 3D printed structure. In this case, uh, of polymeric with ABS, PG, and PLA. It's a particularity of this work is that we are testing in 4-point bending. So this is the structure of the presentation, beginning with the objective, followed by a short introduction to the topic, uh, experimental and numerical parts, because this work also aims to evaluate numerically the different parameters of the joint, such as stiffness, strength, energy, and then the comparison of results and conclusions for future work. So the main objective of this work is to evaluate the 4-point bending behavior of adhesively bonded 3D printed structures. With that purpose, we are going to test 3 geometries: single up joint, hard joint, and single step joint, with 3 adhesions and also with 2 adhesives, which is one epoxy adhesive and another polyurethane adhesive. In parallel, we want to calibrate the numerical models by cohesive zone modeling so that we can apply this methodology and this framework in design of adhesive bonded 3D structures. A short introduction to bonding, which is nowadays widely used for joining in applications that require, for example, to join different materials or to reduce the weight or to improve the aesthetics. And we also know that with the advent of Industry 4.0, we need to produce components with high complexity and customization, with a low cost and with circular economy principles. So, but we have difficulties in the size of the components that we can fabricate by 3D printing. Thus, it is important to know how we can join them. And one of the solutions which has been studied in this work is to evaluate the adhesive bonding between polymeric joints. Some details on the 3 types of adherents. Here we can see 3 printed dog bone shaped adherents for tensile testing, one for each one of the materials, PLA, PHG, and ABS, and also the parameters that were used in the fabrication of this component. I already saw this graphic before today. So here the main issue to retain is that the PLA is stronger but also stiffer than both the PHG and the ABS. So we expect some differences in the failure mode, for example, and in the type of failure of the joint. And in terms of adhesives, we are using a stronger but less ductile epoxy adhesive, which is the Araldite 2015, and a more ductile but less strong Sikafort 7752 from 6. We tested 3 geometries under 4-point bending. We can see here all of the dimensions that we tested, and here the main parameter is varied in the joints, in the 3 types of joints, is the overlap length, basically the length of adhesive between the 2 adherents, and this was varied in values of 5 millimeters, 10 millimeters, and 20 millimeters. We saw some details about the fabrication process. We have a single up joint being bonded, a mix of the Sikafort 77 adhesive, and the joint being cured in a flat surface. The specimens were tested in 4-point bending, as we said before, and we can see here the setup. This is one example for one scarf joint. This is one step joint and another scarf joint. Numerically, we modeled the geometries in Abacus, and we used cohesive elements with a triangular mixed mode law, so that we can simulate damage initiation and propagation in the adhesive layer. And here we can see the setup for each type of the 3 joints. We have 4-point bending setup with 2 supporting rollers, 2 loading cylinders, and the part of the joint where we will have failure either by plasticity of the adherent or by cohesive fracture of the adhesive layer. Some details about the mesh sizes, the bias effects that were used with a more refined mesh near the crack propagation region, and the type of elements that we used, which were mainly strain elements, CPE4 and CPE3 for the slope surfaces of the scarf joint, and a cohesive element with 4 nodes for the adhesive layer partitions of the model. Here we can see some important shapes, one for each type of joint. We have a single up joint, we have a scarf joint with an overlap of 20 millimeters, and one step joint here showing the beginning of failure in the adhesive layer. In terms of results, we will begin by the maximum load. This is the peak of the P-delta curve that we obtained, here either experimentally or numerically, and we have one plot for each type of adherent, PLA, PTG, and ABS. Tables, we have highlighted the lack of coherences in the failure mode, and also the highest effort between experimental and numerical values. Here we can see that we have a good coherence between failure modes. We have only one of the conditions that do not match. We have a significant increase of the maximum load, 5 and 10 millimeters of overlap, and we have a stabilization up to 20 millimeters, which is mostly linked to the fact that the failure starts to occur in the adherent. In terms of maximum effort, it was 8% for one specific condition. And if we move on to the scarf joint, we can also see that there is a good correspondence in terms of failure mode. One condition in which the experimental failure was in the adhesive, while numerically it occurred by plasticization in the adherent. And once again, we have a higher failure load between 5 to 10 millimeters than between 10 to 20 millimeters. Maximum error was also below 10% in this case. In the step joint, we noticed that for our single step geometry, we fragilize the overlap region because we have a sort of cross section because of the step, and we had almost always an adherent failure starting from the shortest overlap. So we have very small difference in maximum load as a function of the overlap length, but we have a maximum effort for an ABS 2015 joint of almost 17%. In terms of stiffness of the joint as a whole, in terms of elastic stiffness of the P-delta curve, here we have an increase from 5 to 20 millimeters for all of the adherent types, and we have a maximum error of about 5% between the numerical simulation and the experimental data. For the scarf joint, we don't have a significant difference with the overlap length. We have significant standard deviation between experimental values, and we have efforts that typically are not bigger than 10%, but we have 2 or 3 conditions in which we have a large error in this variable, which is also prone to error in the measurement. In terms of step joint, also in terms of thickness, there are no significant differences, not a clear variation of increase or reduction with the overlap length. We have also significant deviations, specimens of the same conditions, tested experimentally, but here the maximum errors were not so significant as in the scarf joint. Finally, we want to evaluate the failure energy of the specimen, and this is the area beneath the P-delta curve. So it gives us an idea of the dissipated energy before failure. And if we begin by the single up joint, we can see that we have a significant increase between 5 and 10 millimeters, which is consistent with the increase in maximum load and also with the increase in the failure load, but between 10 and 20 millimeters, the alteration is minimal, and in some cases we actually have a short reduction because the specimen gets more brittle. Here we also have good correspondence, but there were few cases in which we have deviations up to 30-40%. And this is also a parameter that is more difficult to measure because it involves many variables such as the maximum load, displacement at failure, and it's easier to accumulate effort than, for example, when the maximum load itself. The results were closer between experiments and numerical simulations for the scarce zones, and here we have an increase between 5 and 20 millimeters, although bigger between 5 and 10 millimeters. For the step joints, and because of the fact that we have almost always failure in the adherence, there were no significant differences, but once again, we have a good correlation. Here there was some condition that we had clearly some problems that we need to look at, but typically we have a good consistency between the values. In terms of conditions, we compared different joint geometries, we compare different adherents and different adhesives. Between joint geometries, the scarce one is the best to have a good strength in bending, because it combines the strength and stiffness with a coherent energy dissipation. The step geometry performs worse because of having a smaller cross section at the region of the single step, but the least effective was the single arc joint, which is related to a high offset between the adherents, non-collinearity of load, which leads to the worst result. In terms of adhesive, the 2015 was superior, both in strength and the stiffness, compared with the 7752, although this last, since it is more ductile, in some conditions it provides us with a higher failure energy. In terms of numerical modeling, we had good results, satisfactory results regarding the experimental trends, although there were some discrepancies, but we consider this method can be used in the design of this type of adhesive joint. I would like to finish this presentation with some ideas for future work, and thank you so much.